In today's
Very good
workshop,
morning.
good morning, sir. Today's workshop, we are discussing about the flow meters and their testing and the calibration procedures. Today we have with us our esteemed Professor P.K. Suresh, who is the scientist, deputy director from FCRI Palakkad. And I remember that we have done a lot of work under his guidance since last more than 20 years. We are aware of him. Dikshit Saab and myself are very well aware of about Mr. P.K. Suresh. Thank you very much, sir, for giving us this opportunity and sharing your thoughts and your experience, your knowledge with the country persons who are working in this field. We have with us our Joint Secretary, sir, Shri Vineet Mathur Saab, who is also a very nice person who is always helpful for the legal methodology and the technical parts. Being an engineer, he understands the technicality and the technology of the whether it is legal methodology, mass methodology, or the industrial methodology. Sir, we are always thankful to you. You are always helpful to us. We are thankful to you, sir. We have with us our Dikshit Saab, BN Dikshit Saab, who is also very helpful for the legal methodology. He has spent his whole life for the development of the legal methodology. Sir, first of all, I would like to request Shri Joint Secretary, sir, Shri Vineet Mathur, sir, to kindly inaugurate the conference, please.
Yeah, thank you very much, Mr. Ashutosh Agarwal, and a very good morning to all the participants in this workshop today on flow meters and the uncertainties involved. I welcome Sri P.K. Suresh, former Deputy Director of the Fluid Control Research Institute, who's going to give elaborate talk on the flow meters and the uncertainties involved and other things. Now, as far as I understand, I guess all the flow meters and the meters or the utility meters, they form a great level of consumer utility and instrument. And therefore, they are largely available in the industrial units. They are also available in the, let's say, individual units, and maybe shop and establishments also have uh, these use of flow meters. And these have been developing over the years, and the technology has been changing in this particular segment. And we have now a very advanced technology on how the electronic meters and the flow meters, especially, and what kind of flow of the utility or item which is passing through them can be measured, and what kind of calibration and uncertainties are there. Now, as you all know, India is now a galloping economy, and we are going to be one of the great nations in the next 25 years. And therefore, we are modernizing our equipment, we are modernizing our technology, our usage, our ease of doing business or benefit for the consumers, industry per se. So, utility meters, flow meters, they become a benchmark for all the items which are largely going to be very, very important. And these commodities or even energy meters for that meter per se is going to be a great item for probably to capture the calibration or measurements appropriately. I understand there are very few experts in this area, and the Fluid Control Research Institute is in Palakkad is one of the important agencies who's working institution who's working in this area for many years, and they have the latest knowledge and research in this particular area. They have large collaborations also, I understand, with the important industrial and commercial institutions, research institutions in the country as well as abroad. So I understand this is going to be extremely useful session, both for the industry, for the academics, researchers, as well as for common consumers like I am, who is every day have to look into the flow meters and their usage and what kind of measurements are they doing. So with these opening words, I wish this workshop an extreme success. I think that the participants will be raising their questions, and we should be in a position to gather important points or policy issues which require the intervention of the department or the government of India, and we will certainly look into it. I look forward to the lecture from Mr. P.K. Suresh. Thank you very much.
Thank you very much, sir, for your kind words. Certainly, you are always with us, and I look towards you for the betterment of the legal methodology. As we were discussing yesterday, sir, there are a lot of problems in the field of legal methodology. Some infrastructural problems, some resource problems. So we have to see, we have to sit together. We have to find what are the ways we can develop this legal methodology in our country. Sir, now we have with us Shri B.N. Dikshit, sir, Director Legal Methodology. Sir, kindly speak to us and motivate us for these type of programs.
Uh, Sri Ashutosh ji, respected Mathur Sahab, Sri Suresh Sahab, when we think that there is a problem, certainly there is solution also. And if there is no solution, then some scientist people will say that the medium of accuracy of checking of instrument is not correct. So that way the things is there. One point Mathur Sahab has very rightly pointed out that there should be some research paper on every Saturday, Sunday, or whatever the day is there in such type of organization that must be continued, so that who are the people who are doing the research work and doing the taking the interest in that very subject, and they are searching the various books and pages and all that very things, magazine to magazine. After that, they are getting opportunity to tell something about that very subject, and they are not able to say on those very things also. So I think that this is very encouraging even for the junior also. Uh, they should get opportunity to hard being by senior officers, even though they are very junior, but we must respect their knowledge and whatever the work they have done it. So that way the encouragement part comes before us, and we give boost up to the peoples, and they get one way encouragement and incentives that their work has been recognized. So I feel that in every 15 days or once a month, some days should be there on a particular topic, and that covers the all the Root Control Research Institute, NPL, and other organizations and officers from the different organizations, even from the legal methodology, and those who are the other organizations who are attached with the measurement of systems by any hooks or proofs. So they should be also called there. And if some thing is going on, then it is a very good process. And uh, it is just a flow of knowledge and increasing of the knowledge, and we do not have the documentation at present. So if we are writing on any subject, even once a month also. So that will be very, very good and very good things also. Uh, he may be junior or he may be senior also. So this is gives encouragement to the all the peoples. At least some document things will be there. So next time some corrective actions may be taken, and even the senior officer will think that why I have not corrected this point. So people know some things more about the subject, but sometimes they forget to tell about that very thing. So this is very vast subject, and this is not one day job. This is one man itself is a library, but one man cannot be maintained the library. So he has to maintain the records in his minds. So it is better that one place some records and some other lectures should be recorded so that his lecture is recorded at that very point. So he will remember those very things that when he will try to speak to the his best point of view and to the correct point of view, and he will try to give the correct judgment also. I hope that this will lead to us one step ahead, and this will be very good for the all the organizations, academic organizations, laboratory organizations, scientific organizations, and all the legal metrology, RSLs, and various others colleagues also there. So this is the uh, one way we can adopt the future things. By that way, we can improve the legal methodology as well as various other tools. So uh, this is very helpful thoughts given by Mathur Saab, Joint Secretary, Department of Consumer Affairs, and I hope that in future this will be uh, somewhere recorded, and people will be appreciated for those type of things. Another thing is that you see that when you have to start the research work, so you have to start the research work from the beginning. You cannot say that I am uh, not interested to start the research work from the beginnings. Uh, if you start the things from the beginning, only then you can understand the basic of the science, and then you can start the actual practical things to the topmost level in a particular hierarchy knowledge, and then you'll get that type of things and another type of things. So that is very, very important things. Even if you'll go to the uh, PSC classes or MSc classes labs, you'll find that there is a complete hierarchy systems are there. Even in 10 plus 2 also the total hierarchy systems are there. So precautions are also there. But you have to give the maximum preventions, and where the dangerous zone is there, where to prevention is there, and what to do and what not to do, and so many other type of things. So when we have to start such type of flow measurement systems, so we do not know that what is the viscosity, what is the flow rate, what is the uh, this pipe which is made of, how it can wear up, and uh, how much load it can bear up, otherwise it will break down. So many issues are there. So those things must be kept in mind. So when we'll keep those very things, then we will understand the what is the actual speed of the uh, uh, liquid, speed of the pressure of the liquid, and maximum floor pressures and maximum spirit pressures, and the type of the uh, pipes where this liquid can flow, and all these type things, and the temperature etc. may be followed. Even though these are the self bookish type of knowledge, but even bookish type of knowledge also may be recorded somewhere, because these are forgotten every day. So this is also a very valuable thing. So wherever we are starting our this type of things, there also we must place our chart and all that type
टाइम
of
लगेगा,
things.
2 घंटा लगेगा।
हाँ,
शाका में
तो
शाका में
हाँ, तो जहाँ पर भी इस तरह की चीजें आप रहेंगे, वहाँ मैनुअल चीजों को आप देंगे जो है, सर्टनली आप जो है एक लेगेसी जो है आगे आने वाले लोगों को दे के जाएंगे। अपने लिए तो आप स्वयं ही
वैभव,
एक
ये थोड़ा
लेगेसी।
मीटर अलग से अंदर जाके दिखाओ। वैभव, थोड़ा मीटर दिखाओ।
तो आपको पास जो है अपने आप में बहुत कुछ नॉलेज है, लेकिन छोटे लोगों के लिए तो जो लिख पढ़ के आप जाते हैं, उसी को बेचारे बार बार पढ़ते हैं कि आशुतोष साहब ने उस दिन ये बोला था तो यही चीज करेक्ट होगा। ठीक है ना।
थैंक यू
अब
सर।
बाकी तो वो रोज आपके कैलिब्रेशन और अन्य चीजों के मुद्दे में वो इतना आप उनको भटकाए रहते हैं कि एक्चुअल पॉइंट ऑफ कर क्या कैलिब्रेशन होता है, मेजरमेंट ऑफ अनसर्टेनिटी क्या होती है, तो मेनी इश्यूज क्या होते हैं। ठीक है, वो बहुत बड़ा एक सब्जेक्ट होता है, साइंस का मेजरमेंट की थ्योरी है कि आप किसी भी चीज के वैल्यूज को यदि आप करेक्ट मेजर कर देते हैं, तो वो बहुत बड़ा साइंस का पैमाना कहलाता है।
वैभव, ये
ठीक है ना।
अंडर टेस्ट और वैभव अंडर टेस्ट, और जो हम लोग अंदर देंगे ना, वो रीडिंग्स दिखानी है।
हाँ, तो जो
ओके
भी
सर।
आप अपना करेक्ट टेस्टिंग दिखा ले देते हैं
यस सर।
कि ये मान लीजिए कि 100 ml ही क्यों ना है, तो 100 ml को 100 ml आपने दिखा दिया, तो ये अपने आप में एक गारंटी की बात हो गई ना कि आप 100 ml को 100 ml शो कर सकते हैं। ऐसी बात नहीं है कि 100 ml को आप शो नहीं कर
ये क्या
सकते।
पागलपन हो रहा है।
ठीक है, वैसे ही आप जो है कोई मान लीजिए कि 1 kg का ही वेट है, 10 kg का वेट है, 10 kg के वेट का एकदम मास वैल्यू निकाल देना, वो भी अपने आप में काफी इम्पोर्टेंट थिंग्स होती है। तो सारी चीजें आप तो आप डिप्टी डायरेक्टर।
तो दीक्षित साहब, मैं रिक्वेस्ट करूंगा, हम एक्सपर्ट को सुन लेते हैं फ्लो मीटर्स पे।
थैंक यू वेरी मच सर। आई थिंक दीक्षित साहब का कनेक्शन ब्रेक हो गया है। थैंक यू वेरी मच सर। थैंक यू दीक्षित सर। थैंक यू माथुर sir. Sir, we have with us our great friend Mr. P.K. Suresh, who is basically the known personality in this country in the field of this flow meter, CNG, LPG dispensers. Sir, earlier we used to have a lot of training programs at FCRA Palakkad, but since last many years during this COVID and all, we could not organize, and that's why we requested him. And these people are so kind enough. All they are basically working under the Ministry of Heavy Industries, and these people are so nice. Very nicely they used to organize the programs. Sir, we have our own flow meter system. I think Vaibhav, we will show you later on. We start with the expert training, and then at the end of the program, you just show how we are doing this calibration with the weight and the flow meters. Sir, Suresh, sir, please kindly continue. Please. Sir, your mic is off.
Thank you, sir. Thank you for the opportunity. Mathur sir, good morning. Thank you for the opportunity and thanks for the nice words. I'll share I am retired from FCRA. I retired in last July as head of customer care and liquid flow labs. So today I'll be discussing, I'll try to discuss the things about the liquid flow lab and the liquid calibration flow meters. I have already requested the gas person to share his thoughts, maybe in with another opportunity in the next class or something like that. And I'll make Agarwal sir contact that person, and he will do the gas part of the thing. So I am trying to give you a brief on the flow meters, the characteristics of the flow meters, maybe the calibration of the flow meters, and the uncertainties involved in the calibration of flow meters. Measurement and control is a must in the modern industry, especially when you are using automation, artificial intelligence, and such kind of things. The measure and control is the most important factor of any industry to maintain quality, to maintain probably the you can say the profit of the industry, and also to ensure that the people are satisfied, the consumer is satisfied with what is being measured. Then what is measurement? Measurement usually involves using an instrument as, this is the definition of the measurement. An instrument as a physical means for determining the property or characteristics of an object or a system, maybe flow, maybe temperature, maybe pressure, maybe mass, maybe length, or whatever it is. The measurement usually involves using an instrument. And then the instrument serves as an extension of human faculties, and in many cases enable a person to determine these characteristics. So while determining the characteristics or while making a measurement, there are so many things which are involved. One is, we call it as type A uncertainty and type B uncertainty in the measurement of things. Type A uncertainty is which cannot be avoided. I mean, statistics can determine the type A uncertainty. Type B uncertainty involves maybe human error, maybe systematic error, which can be corrected, such kind of things. So uncertainty is a part of measurement, which cannot be avoided, whether it is type A or type B. So when you make a measurement, you try to find out that measurement is how close to the true value. Now, the thing is how close to the true value, how the true value is true, whether the true value is true, which one you consider as true value. And that true value also has got some uncertainty, and how far that is true. So every measurement you take, you are going away from the true value due to the uncertainties. Flow meter and flow measurement is no exception. Here also the same thing happens. As you go on, you are slightly going away from the true value. As technology advances, there is a demand for more and more accurate instruments So accuracy of the instrument is one thing, but how to determine the accuracy of the instrument is another thing. The determination of accuracy is with some better instruments. So if you have an instrument and you have to determine the accuracy of the instrument, you should have another instrument which is better than that instrument. Now, if you make a measurement and you are getting poor repeatability, it always means it is poor accuracy. You are never getting accurate measurement. But good accuracy is always indication good repeatability, and good accuracy is always comes with good repeatability. But good repeatability not necessarily mean that good accuracy. It may be consistently you are getting a wrong reading. So it may be a wrong reading you are getting and you think that it is correct. So that is the most dangerous part of it. Good repeatability is not an indication of good accuracy. So now what is calibration? It's a set of operations that establishes under specific conditions the relation between values of quantities indicated by the device under calibration for a non-measurement input. That is, if you give an input, the instrument will show some reading. So that input is supposed to be the true value and the output is supposed to be the indication of the reading, and there may be some error due to many reasons. It is important that the accuracy of the reference standard should preferably 10 times or at least 3 times than the device of under calibration. Otherwise, you will not be able to determine the accuracy of the instrument under calibration. Now, the traceability. The concept of establishing a valid calibration of a measurement by step-by-step comparison with the better standards up to an accepted national or international level. So the ability to relate individual measurement results to national standards or nationally accepted measurement system through an unbroken chain of comparison. This is important. When legal metrology says that you have to calibrate your instruments once in a year, that means they are insisting for you to keep your unbroken chain of comparison. So they have a comparison level. At RRSLs, they have comparison standards, which is calibrated against the national standards, and they try to transfer the standards to the industry through their regional reference standard laboratories. So when they say that you have to calibrate once in a year, there may be so many reasons by which your calibration may go shift or things like that. But you have to ensure that it is within limits or it is within the accepted norms. Then you have to maintain the calibration records. Records is also important. You have to maintain the calibration records with an accepted measurement system. Accepted measurement system in this case probably for you is RRSLs. You may be spending some money on that, but that is not important. I mean, important in the sense spending money is not, it may become critical if you don't calibrate. Your entire system may collapse if your measurements are not correct. So I am just giving the traceability begins with an unbroken chain of comparisons originating from international level to the working standard or the legal metrology laboratory. And then your traceability is required. You know why it is required. It is for interchangeability of components and parts, support international trade and commerce. If you make 1 kilogram measurement here, and it should not be 1.2 kilogram in Russia. So you should have a measurement which is comparable with international standards, and then only the interchangeability and business will grow. As India is aiming to export items and we are trying to make ourselves, make in India a hub and then make a manufacturing hub for international market, then it's very important that your measurements are correct. So whatever is the measurement, whatever measurement you are making has to be perfect. Otherwise, internationally, you are going to get rejected. So even if you make things, but the things are not up to the standard, then you don't get accepted. So therefore, it is very important that you make the measurements very critically and ensure that the goods are accepted internationally. The measurement hierarchy, it starts from international body to national standard and transfer standard, then working standard, then the measuring equipment. So you can see that the width of this pyramid is indicating the uncertainty associated with that system. As you go down the pyramid, the width of the pyramid again increases at the measuring equipment. You cannot avoid it. It is there. The uncertainty associated with your measurement is there. When you start, it may not be big. You can try to reduce the width of the pyramid, but you cannot avoid the width. It is there. It has to be there because no measurement is without uncertainty. So now I will come to fluid flow. Fluid flow. So the concept earlier used to be when you put a meter and make a measurement, that is correct. So that is not true. The fluid flow is affected by the fluid. As Dixit Sahib has rightly pointed out, it is affected by the fluid, it is affected by the flow, it is affected by the flow meter. The fluid means it can be two-phase, it can be single-phase, it can be with the temperature, it can be with the pressure. The pressure may be varying. There are so many factors involved in the fluid. That is the complication of the fluid flow measurement. Rather, you see, when you make a measurement, a meter or a kilogram, something static. You are making a measurement which is something static. But when you're making the measurement of a fluid, most of the time it is flowing. So you are trying to measure the fluid when it is moving. So the movement of the fluid can affect the flow meter performance. The fluid conditions, like whether it is high pressure, whether it is low pressure, whether it is with in two-phase it is flowing. Two-phase means a flow with liquid and gas, or gas containing liquid or a liquid containing gas. Both these things can affect the flow meter performance. You can see when it's a simple example is when if you see the water meter, when the water supply to your house is stopped, say for example, and when it begins measurement, the air comes through the water meter and you pay for it. I'm telling you, you pay for it. Then the meter runs mad. When the air is flowing, the meter runs mad. It shows the indication as well. I mean, and you pay for it. So the meter performance is not a flow meter which is meant for liquid will measure liquid only. It will not measure liquid and gas. It will not measure gas. If it measures with some indication which is wrong. So that means you might have seen that for making measurement using turbine flow meters or making measurement using positive displacement meters, there are air removers which are kept in that, air eliminators you say. Air is eliminated from the system before you make the measurement. That means the fluid has to be treated properly before you allow it to enter to the flow meter and make the measurement. So the fluid flow is important. That is the condition of the flow. Condition of the flow, when I say condition of the flow, suppose you have a pipeline which has a lot of bends, and immediately after the bends you put a turbine flow meter for measurement, you have a problem, because the turbine flow meter gives you an indication based on the rotation of the turbine flow meter. The rotation of the turbine flow meter is basically proportional to the axial velocity of the flow. If you have any component of velocity other than axial in the flow, then it will make the turbine either rotate at a faster pace, or it will decelerate the turbine, so it will rotate in a slower pace, indicating a lower volume. If it moves at a faster pace, it will indicate a flow volume which is more than the actual, or therefore it can actually measure. It can indicate more than the actual or less than the actual, depending on the fluid flow condition. So therefore, the flow has to be conditioned before it enters the flow meter. the fluid has to be conditioned before it enters the flow meter. And you have to use, most important, you have to use a correct flow meter with a calibrated hierarchy to measure the flow. Fluid flow rate measurements are established. See, the fluid flow meters are affected by the fluid flow rate. That is, the performance of the fluid flow meter changes from flow rate to flow rate. So that is, if suppose you have a flow range ranging from 1 to 100 meter cube per hour, and you try to use a flow meter at 1 meter, the same flow meter at 1 meter cube per hour and 100 meter cube per hour, say for example, let's say 3-inch or 4-inch flow meter, it may not show the same accuracy at 1 meter cube per hour as it shows at 50 meter cube per hour or 100 meter cube per hour. Therefore, the selection of the flow meter or the proper sizing of the flow meter is very, very important, so that it can show the necessary accuracy in the operating fluid flow rate range. So operating fluid flow rate range means, suppose you have a flow meter which is supposed to measure 24 hours. Out of 24 hours, 23.5 hours it measures at 50 meter cube per hour, and rest of the half an hour you are measuring it at maybe 25 meter cube per hour. Then you need to concentrate at the flow rate at which it makes maximum measurement, that is 50 meter cube per hour, not at 25 meter cube per hour. Because why I am saying this is, at 25 meter cube per hour, if your accuracy is minus 0.2% and at 50 meter cube per hour it is 0, then, and if you adjust 50 meter cube per hour flow calibration, it may go to plus 1%, plus 0.1%, which will affect the measurement for 23.5 hours. So therefore, you need to, while making the calibration of flow meters, also you need to be very critical that where you are going to use the flow meter and at what flow rate you will be using it maximum, and that flow rate, what is the error, whether you can keep the error minimum at that flow rate. Why I am telling this is, flow meter performance is dependent on flow rate. Flow rate affects the performance of the flow meter. So fluid flow rate measurements are established differently from counted parts in length mass measurement system. Flow rate measurement system metrology is based upon derived standards, we can say, because see, flow rate, you can say the unit is meter cube per hour. So the meter cube per hour facsimile standard is not available. So meter cube per hour is, you are not keeping it anywhere. Either it's meter cube and hour, you measure it separately and integrate it. That is why it's called derived standards. It is not facsimile standards, it is derived standards for fluid flow rate measurements. Fluid flow rate measurement is important because you do the calibration for the flow range required. Flow range means flow rate range required. So the derived standards for fluid flow measurement system, the metrology is based on derived standards. So the fluid flow meter calibration can be based on volumetric calibration. It can be based on volume tanks, tank provers, can be based on dedicated pipe provers, can be based on small volume provers. Then you have a method called gravimetric calibration, which is supposed to be the most accurate method. Then you have master meter methods. These are basically 3 kinds of methods which are used for the calibration of flow meters. Tank provers, you must have seen. The vessel takes the form of a pipette with a conical end to facilitate the drawing and reduce the risk of air entrapment. So this is a standard vessels normally use standard volumetric tank provers which are used. They are accurate. Actually, they need more systems to calibrate. It's regular calibration of these tanks are required. We have temperature effects probably on the calibration. Maintaining accuracy is a tough task. Measurement of error of level of water in the neck is another uncertainty which it can encounter. So when you are saying this volume tanks, how do you calibrate the volume tanks? If you have a 10-liter volume tank, then you need to use maybe a smaller volume tank to calibrate it, and then finally it reaches the pipette and the or a specific gravity bottle, and the specific gravity bottle is calibrated using a weighing machine. Basically, it goes back to gravimetric system in the end. Volumetric calibration can be static method, dynamic method. I will explain the static and dynamic later. The accuracies are up to 0.1 to 0.2%. This is suitable for total quantity calibration. Maximum flow rate which it can, that is the tank size, due to tank size, it is limited to 1.5 meter cube per second. So now weighing method. Weighing method is based on ISO 4185. That is on-off for actually continuous flow. You can use on-off flow or continuous flow. You can use static or dynamic measurement, or accuracy better than 0.1%. Supposed to be the most accurate method. Here you can see that the flow is maintained through the flow meter, and the flow is finally normally goes into a sump. Sorry. It can be diverted into a measurement tank. The measurement tank gets filled up, and the total mass of fluid collected and the time taken to collect that fluid can be used to calculate the flow rate, mass flow rate, and if you have density, then you can calculate the volume flow rate and total volume as well. So this is the weighing method. The amount of liquid may be determined statically by weighing the collecting vessel empty and weighing the full. That is, before the start of the flow, you make the measurement of the vessel, and then after diversion, you weigh it full after collecting the liquid. The difference in readings is corrected for air buoyancy, and then it is used for calculation. International level facilities for fluid flow for gravimetric system consist of a source of flow, generally a pump or maybe a blower for air, or a constant head tank, and a test section in which the meter and its adjacent piping can be installed, a flow determination system, that is a diverter, a weighing system, and a densitometer. So a source of flow, generally a pump or a blower, that is, you can pump the water directly into the flow meter under calibration and then make the measurement, or you can have a blower for air, and or a constant head tank, which is supposed to be one of the best method. Constant head tank is nothing but a tank inside a tank. So the inside tank is always getting filled with water and supplies water for the calibration of the flow meter. So the level of water supplying to the flow meter is maintained. Therefore, the upstream head of the water is maintained at a constant level. That is why it is called constant head tank. So we will avoid any uncertainties due to the fluctuation in flow if you employ the constant head tank method. A test section in which the meter and its adjacent piping can be installed. After the tank, that is, the source of flow is a tank, supposing that the source of flow is a tank, and then you need to have a test section in which the meter and its adjacent piping can be installed. Meter installation needs upstream length, downstream length, a system to remove the air. All these things are required in the calibration system, and proper assembly. Proper assembly means the assembly of the meter as per the manual of the meter. The flow determination system, it consists of a diverter, weighing system, and a densitometer. Basically, it's a timed collection of the fluid that flows through the meter being calibrated. The collected fluid is converted to mass flow rate using the collection time. The volumetric flow rate through the meter can be determined via the corresponding temperature and density. I will now we have a water flow laboratory in FCRA. I'll just show you the water flow lab video. So you can see that this is the diverter system. The maximum flow through the facility is 5,000 meter cube per hour. So the flow meter is assembled here. Unfortunately, I don't have the figure of a constant head tank. A constant head tank is outside. This is the system in which you assemble the flow meters. This is the system by which you determine the flow rate or flow volume measurement. So there is you can see there are two systems. One is a 20-ton system and one is a 2-ton system here. Here it is a 2-ton system and a 300 kg system. Agarwal sir, if there is some questions, they can interrupt me. I can always answer. Somebody has a question.
Sir, very good, sir. So certainly we will take the questions, but immediately after your presentation or this lecture, so that we will take one by one easily. Otherwise, it will be difficult to take in between.
Okay.
Please,
Okay. So because I am just giving my lecture sort of thing, and I don't know whether people understand it or not. That's why, yes, that's okay. This is the system in FCRA in the water flow lab. You can see, as I have been telling you, the diverter system is basically very simple. So you have a flow coming from the upstream of the meter here, and it passes through the meter and it comes to the diverter. It normally goes into the sump which is seen here. Whenever you want to make a measurement, you actually divert the flow into the weighing tank. And the point at which you make the measurement or start the measurement is known. And the point at which when you divert it back, when the weighing tank is full, you divert it back. And then you know the time for which the collection is made. You know what is the total collection in the weighing tank. And then it becomes very simple. I mean, what is the indication of the meter? You know the meter reading, you know the total volume collected or at what flow rate it is collected also you know. And then the weighing machine. Here, the weighing machines are selected in such a way that you get maximum accuracy for the collection. That is, if your flow rate is very low, then you always go for 2000 kg, and they also have a weighing machine of 300 kg and lesser if the flow rate is very low. Micro calibration, I mean micrometers are also, very low flow rate meters are also calibrated here. using weighing machines which are of the order of 2 kg or maybe 500 grams. They have different kinds of weighing machines used for lower flow rates. Higher flow rates, they can go up to, I say they because I am a retired person. So we can go up to 20 tons here and 2 ton system, and the sump capacity here in this case is 320 meter cube. This is called standing start and stop method of calibration. That is it. You are not stopping the flow for making the measurement. You are only diverting the flow for making the measurement. The fallacy of this system is that if you want to make a total flow, like a PD meter you want to calibrate, and the PD meter has to be stopped to make a measurement, then you cannot stop the flow here. So therefore, you have to have another system which is called standing start and stop method, where you can calibrate the PD meters and other kinds of things, where it is more important for you to find out the total volume rather than the flow rate at which it has happened. So the maximum flow rate attainable is 5,000 here. The maximum line size which can be tested in the water flow lab is 900, and the flow rate with the 0.1% accuracy, you can go up to 1,800 meter cube per hour. From 1,800 to 5,000, actually it is not gravimetric system, it is mastometer method, and the accuracy is limited to 0.25%. And 5,000 to 15,000 meter cube per hour, we have another flow system which I will show you later, which is about 0.5% accuracy. So what I have been telling you was, in this system you are using gravimetric system for measurement, which is supposed to be the most accurate system of flow meter calibration, but it has its own limitations. In this particular water flow lab, they are using standing start and stop method for the calibration, wherein you measure the volume which is collected or the mass which is collected in a weighing tank for a specified time duration, and then the calibration of flow meter is done at different flow rates throughout the flow range. That is, you have a flow meter which is to be calibrated from 50 to 100 meter cube per hour, or say 10 to 100 meter cube per hour. You do the calibration at 10, you do the calibration at 20, 30, 40 at different equal intervals, and you concentrate more on the flow rate at which the flow meter is being used maximum, so that you can minimize the error at that point and make the flow meter more effective, more accurate during its course of service in the industry. So this is the water flow laboratory which uses gravimetric flow system. Here the flow meter which is calibrated, mass flow meter is calibrated, turbine flow meter is calibrated, orifice or venturi or differential pressure, any kind of differential pressure flow meters are calibrated, and you can make the system adapt the system in such a way as to calibrate any flow meter at any flow rate within the specified accuracy. We have that kind of flexibility in this system. This is basically the constant head tank here, and you can see that there are different pumps here. The pumps are pumping the flow through the filter into the tank, and the tank is kept overflowing, which comes back into the sump. The tank also supplies flow to the flow meters. Here are the test lines. These are the test lines. So you have a 150 mm test line, 200 mm test line, then 600 mm test line. All kinds of four different test lines are there, in which can be reduced to any size of your requirement. This is the schematic of the system. You have a 20-ton weighing system. This is the photograph which I have shown you earlier. This is a 2 ton system. This is a 20-ton system. So here, if you take the uncertainties in the measurement, before I go into that, so let us check the uncertainty of the system. One is, you can see you make a measurement of mass. When you make the measurement of mass, you have uncertainty of the weighing system. You have uncertainty of the calibration of the weighing system. You have type A and type B uncertainty of the calibration of the weighing system. And you also have calibration of the densitometer, which converts it into volume. So the uncertainty of the density comes into picture, the uncertainty of the weighing machine comes into picture, uncertainty of the mass which is used for the calibration of the weighing system also comes into picture. How you trace the mass to the national measurement system is also a problem. The uncertainty of the national measurement system also comes into picture because you are taking a smaller weight to the national measurement system, use comparators to calibrate the calibration weights for calibrating this particular system there. Then you have the uncertainty of the national calibration system, you have the uncertainty of the mass, you have the uncertainty of the mass comparator, you have the uncertainty of the calibration of the weighing machine as well. So different components of uncertainties are involved in this kinds of measurement. That's why I told you a measurement is impossible without uncertainty. Every measurement has an uncertainty. Every measurement which you make has an uncertainty. So then the mass part, if you cover, then you have the density. Density you measure using densitometers. The densitometer is calibrated against another density system. So that density system is calibrated against the standard density fluids. So the standard density fluids are supplied by some other organizations which calibrate against international standards. So the density is the three steps away from the international standard. So therefore you have the uncertainty of all these three steps. Remember, I'm not saying that these are all large. These are all small uncertainties, but uncertainties, the root mean square value of all these uncertainties contribute to the error of the meter. Okay. So therefore, the volume, the mass, now you have the mass uncertainty, you have the volume uncertainty, then you have another uncertainty where you make the timing measurement. So when you make the diversion into the weighing tank, some of the water which tank, when you make the diverter back into the sump, some of the water which should have gone into the weighing tank is going into the sump. So the uncertainty of that particular volume which is going into the mass of water which is going into the sump when it should have gone into the tank, and mass of water which is going into the tank when it should have gone into the going into the sump when it should have gone into the sump should be equal. If this is equal, thing is perfect. There is an experiment in ISO 4185 which determines this is called a timing. The timing error is a part of the error, systematic error, which can be determined and included in the uncertainty part. I've shown you the water flow laboratory. Now you have another method called standing start and stop method. In this method, the flow through the meter is accelerated as quickly as possible from the rest to the full test flow rate. At the end of the test, the flow is rapidly stopped. That is, whatever is coming through the meter is directly going into the weighing tank. There is no diversion involved in this. Test time is sufficiently long in comparison with the acceleration and deceleration periods of the accuracy is not affected. The oil flow lab method uses this particular system. In the oil flow lab, earlier Dixit Sir was mentioning that the fluid viscosity affects the performance of the flow meter. So in order to overcome that handicap, we have a multi-viscous flow lab where you can vary the viscosity of the fluids. Excuse me. This is the weighing tank. There's a 10-ton weighing system. There is a 2-ton weighing system. This is where you assemble the flow meters. The 2-ton system, you can see that there is no diverter. The flow which is coming from the flow meter is directly going into the tank. And there is a valve here which can start and stop the flow. There is an on-off valve which will start or stop the flow. Whenever you want to make a measurement, you start the flow. Whenever you want to stop the flow, you can close the valve and stop the flow. Here, you can see that there is a reservoir. The oil which is used is called Exol D80, which is very similar to ATF. And you have flow range up to 650 meter cube per hour. You can calibrate meters up to 10 inch here, and the uncertainty of the order of 0.1%. Uncertainty in volume is better than 0.05%. And you have two test lines, a 200 mm and 100 mm test line, which can be reduced to any size as per requirement. I'll show you the
Oil flow lab
video.
is a world-class facility designed for
Now, the uncertainties, if you check the uncertainties, basically you are finding out the flow rate using a mass which is collected in the weighing tank, a final mass and initial mass. Final mass and initial mass will, the difference will give you the mass of fluid collected, buoyancy correction factor, and density and time. These are the points of uncertainties involved. So as I have explained, the weighing machine calibration uncertainty affects the measurement. The uncertainty in the standard mass, calibration of standard mass affects the uncertainty, final uncertainty. The buoyancy correction factor is a factor which is used. That is basically when you are calibrating the weighing machine using mass, it displaces some amount of air, which applies a certain amount of buoyancy force on the weighing machine and the indication or weighing machine indication. But when you are using water or another fluid to fill in the tank, the amount of air displaced is different. So therefore, the buoyancy effect will be different. So we make a correction. There is an equation by which you can find out the buoyancy correction factor depending on the density of the fluid, and that is applied here for finding out the mass. And you have density, you have time. So the mass and time and density will give you the flow rate. Mass by density will give you the volume if you want the volume. Mass flow meters can be calibrated directly against mass. So this equation covers everything. So mass flow rate is covered, volume flow rate is covered, mass is covered, volume is covered. Simply you eliminate the terms which you don't need and compare with the indication of the flow meter, which will give you the calibration of the meter. If you need to do the correction, and there is a provision for correction of the flow meter, you can always do the correction, but you have to be judicious while doing the correction. The correction is not applied. First, you have to find out the general behavior of the flow meter before you correct. So whether it is linear, whether it is scattered, or whether it has a slope. If it has a slope, what is the slope? And if you adjust the flow meter at a particular flow rate, what will happen to the other flow rate accuracies? All these things has to be considered before you make the final correction on the flow meter. After you correct the flow meter, you need to verify the accuracy of the flow meter once again, so that you have to ensure that it is repeating and no error has occurred during the correction or the calculation. So overall uncertainty is better than 0.1% in the flow rate in these gravimetric systems. Now, you have another method of calibration, which I have mentioned earlier. At FCRI, we don't have pipe provers. Instead of volume tanks, it is not practical to use very large flow meters capacity flow meter. And if you have to collect the volume of 1 minute duration, you just calculate 10,000 by 60. So that much of volume, that much of huge volume tank is required, which is not very practical, because if you install such a huge volume tank, then you have to calibrate that volume tank. For calibrating that volume tank, you need to have another volume tank, which has to be calibrated again. So it's not practical to maintain the traceability, as I have mentioned earlier, to maintain the traceability and therefore the accuracy of the volume tank if you are using very large volume tanks. So in order to overcome that problem, there are pipe provers which are used for the calibration of large size flow meters. So from a flow meter, whatever comes through the flow meter passes through a calibrated length of the pipe. And you have a displacer here. Then the displacer is displaced from one point to another point, and the volume between the displacers is fixed and it is calibrated. Therefore, the volume indicated by the flow meter can be compared with the calibrated volume between these two indicators or detectors. When the displacer moves across this detector, it gives a signal and it moves slowly through the pipeline and it reaches here and it moves from this detector. It can be, generally nowadays they are using optical detectors, which is not touching the fluid or neither the displacer. It finds out whether displacer has passed through this detector. So when, at the point of passing this detector, the volume is known. So between these detectors, what is the flow indicated by the meter is found out. That is how you find out the volume, total volume passed through the meter at what flow rate. So how much time it is taken for the detector to move from this place to this place is also known. So 10 liter, so this is a 100 liter volume and it takes 10 seconds. So then it is 10 liter per second is moving. The fluid is moving at 10 liter per second. So the prover has to be corrected for pressure and temperature effects of volume of the prover and the meter. So there are different kinds of correction factors which are applied in the prover, which is one is effect of pressure on the steel, effect of temperature on the steel, effect of pressure on liquid, effect of temperature on liquid, then the combined correction factor of CPS, effect of pressure on steel, effect of temperature on steel, effect of pressure on liquid, effect of temperature on liquid. So combination of CPS, CTS, CPL and CTL is used for finding out the final actual volume from the prover, which is to be compared with the indicated volume of the meter. So if you see, there are different kinds of provers. One is unidirectional prover, in which the flow comes from only one direction from the meter. It passes through the calibrated length, and it means it pushes it's normally a ball or something which is prover calibrated volume is this much. So if it is coming through this, it's coming through the meter, then it comes through the prover. It moves from here to here and then it moves back to the main system after calibration. So the ball or whatever is moving across this will fall here and then go back to its original position when you take the next run. I hope you can decipher the picture and see it. I don't know. It's not very big. Can you read the picture, sir?
Yes, sir. We can, sir. We can.
Okay. So the flow, the flow comes from the meter. It passes through the pipeline whenever you want to make a calibration. Otherwise, you can close this valve and the flow generally goes into the pipeline. If you want to make a calibration, you pass the flow through the meter and then it comes through the prover. From the prover indicator is here. That is, this is the calibrated prover volume. As you can see, this is the calibrated prover volume. And the flow passes through this and comes through this and goes out. And then you have bi-direction, comes through this and then goes to the original pipeline. Then you have bi-directional prover. Bi-directional prover is, it can move in both directions, and here the ball can move from here to here as well as here to here. Only thing is you divert the flow at this point. There is a diverter valve which will divert the flow from one direction to another direction when it comes here. So the principle is same. The installation of this prover or space required for this prover and all are very high. Therefore, it has developed into a prover has been developed into small volume provers with internal valve and then external valve. This principle is same. That is, whatever is passing through the meter is getting passed through a prover, calibrated prover volume, and then you compare the volume with the volume of the prover with the meter. Now you have a question how we will calibrate the prover. The calibration of the prover can be with water draw method. It can be gravimetric water draw method or it can be volumetric water draw method, in which water is filled into the prover and then it is getting collected. The calibrated volume of prover volume is getting collected in calibrated tanks, standard volume tanks, and then you find out the actual volume of the prover, pipe prover. The pipe prover volume is coming here and it is getting collected in the volume tanks through this, either in this or this, and then you find out it can be using a standard volume tank, it can be used in using a standard gravimetric system. You can use a gravimetric system also to calibrate the pipe prover, but uncertainties involved will be there. You can use a master meter also to calibrate the prover. Now, finally, I'll come to the master meter method. Excuse me for a second. Before that, the master meter method is used in the large water flow laboratory of FCR. I will show you the video on the large water flow laboratory. In this system, you can, sorry. In this system, you can see that the master meter is utilized for the measurement of the system. That is a meter which is calibrated in the these are the master meters which are used for measurement, and these meters are calibrated against the gravimetric system in the water flow laboratory. So, but of course, the uncertainty is of the order of 0.5% in this case, not 0.2 or 0.1%, as has been the case in water flow laboratory. The master meter method is generally used for flow meters of larger sizes, and this laboratory can go up to 15,000 meter cube per hour. And flow meter sizes up to 3,000 were calibrated in this laboratory. But of course, as far as the 3,000 meter is concerned, the 15,000 is not a huge flow rate. But in our country, this is the biggest available. So therefore, one has to be satisfied with what is available rather than looking for something which is not available. So that is a master meter method, which I have. A meter which is of highest accuracy is assembled in series with the meter to be calibrated, and that is used in the indication from the master meter is used to calibrate the master meter to be calibrated. So this is a metering skid in the ship with the 16-inch pipe roller. You can see how much space it is occupying in that. So sometimes in offshore platforms and ships and all, you may not be able to find out because space is very costly there. So you may not be able to find out such kind of space. Therefore, people have shifted to small volume provers. And my presentation is complete, sir. I mean, rather, I'm open for questions.
Thank you very much, sir. Thank you. Thanks a lot, sir. Sir, we have very few questions, but sir, before that, actually, first of all, I think we should take the question first, and then we will move for other things.
Okay. Okay, sir. Okay, sir. Okay.
Sir, there are some of the participants are requesting for the presentation. If you kindly share the presentation with the videos, it will be good for the participants.
I will send you, sir. I will send you. We will definitely send you. If you're not able to get it from here, I will send you. I'll send to your mail. Sure.
Please, sir, please.
Okay. Okay, sir.
Sir, one participant is asking a question. They are calibrating 1 liter per minute to 20 liter per minute.
Okay.
And they use maximum range balance and its accuracy and its best list count.
I did not get the question. Can you repeat the question?
Actually, no, this is not the question. This is the information actually. They are using the best accuracy balance and best accuracy list count. Next, sir, will the temperature of water contribute to uncertainty in prover-based method?
Uncertainty in?
Uncertainty in measurement of uncertainty in measurement of this flow range.
It will not affect to that effect because see the in this gravimetric system your temperature variation is limited to 1 degree per hour. The sump volume is designed in such a way that for the maximum flow rate, the transfer of energy, how do the temperature gets increased? It is from the pump, it is from the atmosphere. So both these things were considered while designing the sump volume, and the temperature during the calibration will not go beyond variation will not go beyond maybe around 1 degree per hour. No, much less than 1 degree per hour. But however, even if it is affecting the volume density of the fluid, the online density measurement is being done to avoid any such uncertainties. Therefore, it will not affect the performance. Temperature of the fluid may not affect the as such your meter per meter. Only the measurement it can affect. Meter it will not affect, because temperature variation is too low to get affected. So you are using it at 20 degrees centigrade and 100 degrees centigrade and calibrating it at minus 15, then it may affect, but otherwise it will not affect. It will not affect.
Okay, sir. Thank you. So the next question is how to convert mass value of water which is measured on weighing balance to volume?
Mass by density.
Yes.
Mass by density.
Yes. Is there?
Density.
Yeah.
You will
That's,
get it from but density you will get from your densitometer. Mass you will get it from your weighing machine. Mass divided by density will give you the volume.
yes, sir. Sir,
Yes, sir.
is there any alternative for Z factor?
For
Z factor.
Z factor,
Yeah.
you mean buoyancy correction factor?
Sir, we know this about the Z, we call this zero.
Zero.
Sir, actually, he has mentioned Z factor, and I am right now I am not able to recall this Z factor.
Z factor. I am sorry, I am also not able to recall what is Z factor.
Okay, we will do it later on. Sir, one another
Okay.
question is how to convert mass value of water, which is measured on weighing balance. This is already done, taken.
Okay, this is done. Mass by density.
Yeah, this is already taken. Yeah, this is now the next question is which uncertainty taken in part for calibration method of master meter method
Which uncertainty?
of which uncertainty taken in part for calibration method of master meter method. Suppose somebody is calibrating through master meter, what are the parameters which will affect for uncertainty?
Okay. The first is the master meter uncertainty.
Hmm.
The master meter is getting calibrated somewhere.
Yes.
So the calibration certificate of the master meter will mention that uncertainty. You have to take into account that. Then you have to take into account of your system. The type A uncertainty of your system. So that's all.
Okay. So, sir, what is the difference between flow meter and bulk meter?
Flow bulk meter is also a flow meter, which generally gives you the bulk flow, that is total volume. Say, for example, PD meter, you call it bulk meter. But there is a DP meter, an orifice meter, you call it flow meter. An electromagnetic flow meter, which is generally given as flow rate. It's electromagnetic flow meter is considered as flow meter. Both are same. Bulk meter is also a flow meter.
Sir, next is for doing calibration of vehicle tank, is proving measure better or flow meter is better?
That you should be able to tell, sir. I mean,
No, sir. Technically, if we see technically, what do you feel?
sir, if you see technically, say that depends. I mean, see how accurately you are. How do you do the calibration of the vehicle tank with a meter? With a meter with a better accuracy can be used to calibrate the vehicle tank. Nothing prevents you if it is within the limits as per rule. The uncertainty of the master meter is within the limits as per rule, then you can use. The uncertainty of a tank calibration is within the rules, that also you can use. Which is better, less time consuming, you can select. I mean, nothing
Okay.
prevents you technically.
Okay.
Legally, I don't know.
Okay. What is a master for very low range, like milliliter per minute or yeah.
You have mass flow meters, mass flow comparators, which are used for such kind of flow rate applications, and there are flow meters which are used in medical industry for finding out such. There are many manufacturers who supplies you that. If we can give the specific requirement, then I can tell him better, which is the best meter.
Sir, for example, when you are giving some glucose or some medicine to a patient, at what flow this will inject into the patient?
That diffusion flow meter is there already there in medical. There is we do calibration of diffusion flow meter, which is very difficult to do the calibration because the flow rate ranging from milliliters per maximum flow rate is milliliter per hour. So you can imagine, I mean, because you have to prevent the vaporization of the fluid, which is used for calibration during the calibration. That is one of the major errors which could encounter. So we are doing it in a very closed atmosphere, which is a very controlled atmosphere without evaporation.
Okay. So how to validate mass flow meter with weight scale? That means weighing scale. How?
It is direct, sir. I mean, what is indicated by the mass flow meter is compared to the weighing scale. That is direct, which is a weighing scale applied with the buoyancy correction.
Yes, sir. Yes, sir. Very good. So directly they can take the weight.
Yeah, directly you can take the weight.
How to mitigate errors between them?
Mitigate errors.
Between the readings of the flow meter and the weighing machine.
So that you have to do a proper calibration of the weighing machine, and you have to ensure that ensure that you are not hurrying through the calibration. I mean, you have to allow the flow rate to settle before you do the calibration, and check it maybe 5 or 10 times at the same flow rate, so you can mitigate both kinds of errors, systematic as well as type A and type B errors. You can mitigate.
So what to calibrate and what factor to be calibrated? For this, I think we are calibrating actually the mass flow meter with the help of the weighing machine.
Yeah. Basically, mass flow meter can give you mass flow meter based on the mass flow meter principle. The Coriolis principle gives you the mass output, and the what you can the vibration gives you the density. These are two different factors which are coming out of two different principles. So mass. What was your question, sir? So
Yes.
can you repeat the question once again?
Sorry, sir. Please, sir.
Can you repeat the question once again?
Sir, they are just saying what do calibrate and what factor to be calibrate.
If you're calibrating it against mass, you
Yes.
change the mass factor. You change the mass factor. If you are calibrating it for volume, then you change the volume factor. You don't have to fiddle with both mass and density. So either mass or volume. That will do. That will.
Okay. So next question, is it possible in gravimetric method for milliliter per minute range?
Possible? Yes, it is possible. We are doing it.
Okay, very good. So can we calibrate flow meter with ultrasonic flow meter?
Which flow meter you want to calibrate with ultrasonic flow meter? It depends. I mean.
So maybe like volumetric rings type or something. I think we can calibrate.
We can use it, but the uncertainty of the calibrated meter will not be better than the uncertainty of the ultrasonic flow meter. We can do, for that matter, you can use even rotameter to calibrate mass flow meter. So, but uncertainty, but it will defeat the very purpose of using a mass flow meter. So if you have a ultra accurate flow meter, then you need to the calibration against the ultra accurate system.
Very good. Thank you, sir. Sir, while measuring flow meter, while measuring flow using viscous liquid, which method is better as far as accuracy is concerned? The prover-based method or gravimetric method?
Calibration. See, calibration of the meter, gravimetric method is better always, but it is very difficult to get. Suppose if you have a highly viscous fluid, you don't have a calibration system for that. So that is the problem. So there you go for a rather compromise. I mean, you do master meter method or you do prover. If you have a large flow rate and huge viscosity, then you always go for prover rather than gravimetric, because gravimetric systems don't have multiple viscosities of large variations.
Okay. So our state government officers are requesting to organize these training sessions at FCRI.
That you can contact Mr. Sundar Vadivel, who is director in charge at the moment. I will also tell him. Said you are the right person, sir. I mean, there is no better person than you to organize that.
Thank you, sir. Thank you. I will request, sir. Sir, how to intermediate check in master meter?
Intermediate check, you can have, if you have two master meters, you can check between them. That is the only way you can do it. Otherwise, if it is a known volume or something is there, then you can check against it, and then find out. Or if you have a machine, weighing machine of better accuracy you encounter, you can check using that.
Okay. So for MS and HSD flow to calculate temperature correction during calibration, sorry, for MS and HSD, MS means this,
Water spirit.
yeah,
Wet
and
control.
how to calculate temperature correction during calibration.
Do you actually do that? I'm not sure. While using the verifying can, you don't normally do the temperature correction, no? I mean, I don't think so. You
In that,
you can do it. If you need, you can do it. That is not a problem, because all these factors are available in API. That is for correction for temperature. Pressure will not affect because you are doing it at same pressure. So pressure will not affect, but the temperature correction you can do it using API table. That is at what temperature you are collecting. That is effective temperature on steel and effective temperature on that particular MS or HSD is available in API table. So that you can do it.
can we calibrate flow meters using pipe provers in Northeast?
Why not? Yes.
Okay. Can we calibrate the mass flow meter using EM meter, electromagnetic meters, as meter for flow rate?
Same answer prevails, sir. I mean,
Yes. What testing to be done for dispensers for model approval and FCRI? All testing as per OML recommendations.
OML recommendations.
Yeah.
All the tests as per OML.
Yeah, you are doing. So we have this testing facility at RR as well. I would just like to show you. It's I think we unfortunately we do not have the right now very good facility to show you. But one of our officer will show you that how we are doing. So this is the display of our master meter. Can you bring it closer to the meter? Yes. Yeah, this is the master meter reading which we are taking over here. As actually this whole facility was established by FCRI. I am always thankful to FCRI which has actually developed all these facility, mass flow meter, water meter, everything we are having with the help of this FCRI. So this is the observation table. This is the observation where we are taking. Now you show the flow meter, master flow meter, and the flow meter which is under test.
I'm not seeing it, sir. I mean, I'm not able to see it.
Again, I will again show you. So this is the master flow meter under test, which we have installed over here in between the line. Can you see, sir?
No, sir.
How to share? I think, okay, I cannot share because he has.
He can share. He can probably share.
No, he will not be able to. Yeah, he can share, but I think right now not. Sir, okay, you are not able to see this mass flow meter, sir?
No,
If I just
I'm
take it on the stage.
No, sir. I can see your beautiful face only.
Thank you, sir. This is the mass flow. Actually, sir, if we just go behind the screen, I think this is also very small. We cannot see the screen. Anyway, I think Vaibhav, we cannot show this all. This is the sir master. This is the master flow meter which we are showing now. This is under test. And show us the mass flow meters which are tested, calibrated at FCRI.
Okay.
So we have the tested mass flow meters calibrated from you only.
Okay, sir.
These are the mass flow meters, sir. We have calibrated last and now again we have to send.
3 inch and 2 inch, I think.
Yeah, half inch, 2 inch, and 4 inch.
4 inch.
3 inch, sorry.
3 inch, 2 inch, and half inch, right?
Yeah, 3 inch, 2 inch, and half inch.
Half inch.
So these are the mass flow meters. So we have also developed this weighing facility. But we do not have this flying start and flying stop facility we don't have, but we can collect the water, and then
Okay,
with
fine,
the
okay.
speed of time, we can say this is a 2-ton capacity which we have developed. And now we will be requesting FCRI to kindly make this, develop this facility of flying start and flying stop, so that we can also do the calibration in the same way.
Okay, okay.
This is the facility. And sir, we also have this endurance test. Can you show the endurance test?
For water meters.
Yes, sir. For flow meter, sir.
That's
Because
what.
model testing we have to do at least 1 lakh times. This is the
Yeah, yeah,
this is
yeah.
our, sir, this is our endurance test facility. So these are the things, sir, we have for the mass flow meters and all type of flow meters testing facilities. But most of the testing and calibration is being done by FCRI, so we are relaxed. Thank you, sir. Sir, this is basically FCRI is having the one of the best facilities I think in the world.
But not recognized properly, sir. Even
No,
now.
but no, sir. Everybody recognize. Everybody recognize, sir. Sir, some of the few other questions, sir. Functional check to required in gravimetric method.
Yeah, you can do the functional check of flow meter or the gravimetric system. Which one?
Okay. During the start and stop method, how to calculate the diverted time method and what could the error?
You can have actually basically it is not diversion. It's the valve is closing or opening. During closure or opening, you can have a signal from the valve stem to initiate the counter. I mean, time counter. So the time of operation, approximate time of open position you can get. That is when it closes, you can have a photo switch across the valve stem, and when the valve position, there can be a positioner as well. When the positioner moves to that photo stem, the timer will start, and when it moves away from that, another timer will stop. So the time between these two will give you the time of collection. Approximate time of collection you will get, and you can calculate the flow rate.
Okay. Some of the officers are asking some questions which are related with us only with the central government. We'll take it later because this is a technical session, not the official discussion. So I am not taking it here. And
If you have any further questions, they can you can send it to my mail. I will answer, sir.
certainly, sir, I will send it. Sir, one another very important point which I am just observing since last many years. Actually, sir, what happened when we used to take the observation on a weighing machine? We always used to take the weight, not the volume, from a weighing machine. Because sir, weighing machine can give us the weight as per the load cell technology or whatsoever the EMFC technology. We can take the weight of the commodity or a product placed over it. But there was some years back, there was some confusion was there that this weighing machine may have a software, and with inserting this density of the liquid, density of the water, or some other factors which are actually responsible for that particular liquid, we can convert it into the volume, and the weighing machine can give the readings in volume. So, what do you feel? Whether it is a right option or what we should? What do you? First of all, do you understand what I want to say?
Yeah, I understand, sir. I mean, if you have an online density, then you can feed it into the weighing machine and then directly get the volume out of the weighing machine. I don't think that is required, sir. I mean, because your density you can always measure, and then an Excel can do all the tricks for you. So it is better to take the mass directly, so that you take it becomes what do you say? I mean, it neither becomes a weighing machine, it neither becomes a volume machine. So you can take the weighing machine mass and then oh, secondary जैसे होता है ना
And then convert it mathematically in the
mathematically to volume.
yeah, that is a better way.
That's a better thing.
Yeah, that is better way. So I think, sir, thank you very much. We have some more questions. I will send you in your mail and we will reply in the groups or in the next batch.
Thank you.
Sir, the most important point is we wanted to take your lectures or your learning about the CNG dispensers, LPG dispensers, and other type of new technology like LNG, which is also very famous in India, hydrogen dispensers. So how to use, how to test all these things. If you kindly put some light on these equipments, maybe maybe in the next session at any day, whenever you are comfortable, because every Saturday we used to have this program. At as per your convenience, we can arrange at any day, and you kindly let us know on which day we can do. Similarly, we would like to have one lecture or one understanding, one seminar, workshop on water meters, one workshop on other parameters, because FCR actually is actually the mother of this fluid system in the country. In India, I hope that earlier you were there in the whole Asia, but now maybe some other laboratory, and you know better than me. But otherwise, in India, we always look towards FCRI for all these flow, and gas measurement is also very important, sir.
Okay, sir. For as far as gas is concerned, I think Shivaprakash can help you. I'll tell Shivaprakash also. He can conduct a session definitely on the gas flow measurement. I mean, air flow measurement. I will tell him also.
Please.
Maybe I will give a hint that you will call him. So you
Yeah,
can
I'll call him, sir. I'll call him.
And,
It's LPG, CNG.
LPG, CNG. CNG also, why don't you contact the Moscow Money can give you on CNG.
Okay.
Moscow Money is the right person for CNG. LPG,
Okay.
of course, K. Suresh can give. I can also give, no problem.
Oh, so sir, next time, next week, if you can, whenever possible, LPG and some other parameters which you can take. First, you take, please, sir.
Sir, why don't you ask? I can take, no problem. I can take. Okay,
Okay.
I will let you know. Next week, next 2 weeks, I may not be available.
No problem.
So afterwards, I can definitely do, sir.
Please, thank you very much, sir. So with this,
Thank you for the opportunity. I convey my regards to Mathur Saab and Dikshit Saab, and wish him a happy retirement life, peaceful.
thank you, sir. Thank you. First of all, I would like to thank Mathur Saab, Dikshit sir, and my great friend, Mr. Suresh. Thank you, sir. Thank you for your this enlightening lecture. And certainly, again, in future, we will take your help to enlighten our participants. Thank you very much, sir. Thank you.
Bye. Thank you.
Thank you.